stratigraphy of SPA, insights from pyroxene composition and distribution. Daniel? Laser pointer, and that moves the.
Great, thank you. Once I have slides, I'll begin. Perfect. So we've been looking at the magmatic evolution of SPA, and specifically some of the insights we can gain into these processes by looking at Mafic Mound. So Mafic Mound, for those who aren't familiar with it, is an unusual positive topography feature that's located kind of at the very center of the lowest topography region within SPA. Mafic Mound was first discovered due to its very long wavelength 1 micron bands in work done by Carly Peters using Clementine data. So using more recent M-cube data, we've confirmed that these long wavelength 1 micron bands are due to high calcium pyroxene bearing materials. So the first thing we want to do is compare the high calcium pyroxene bearing materials we see in Mafic Mound to other lunar high calcium pyroxene bearing materials, namely Mare and cryptomare basalts. So we've conducted a small survey of Mare and cryptomare basalts from within SPA in order to do a direct spectral comparison between the Mafic Mound materials and these basalts. So here we're showing representative spectra of these materials from Mafic Mound in red, and then the cryptomare and Mare materials in gray and black. So what we immediately see is that Mafic Mound materials are consistently brighter than these Mare basalts for both immature materials exposed in fresh craters, as well as well-developed soils. So what this tells us is there's an inherent brightness difference due to the mineralogy of these materials. So we're probably looking at a situation where Mafic Mound has more bright minerals like plagioclase in the mineral assemblage. We're really also interested in looking at the pyroxene compositions of these materials. So to do this, we want to measure the band centers of the 1 and 2 micron band. The reason we do this is because band centers for pyroxenes are systematically related to the iron, magnesium, and calcium content of the pyroxene minerals. So generally, as you shift from short wavelengths to long wavelengths, you increase your calcium content in the pyroxene. So to measure the band centers, we remove a continuum from each spectrum and then fit parabolas to the 1 and 2 micron bands. When we plot the 1 micron band center versus the 2 micron band center for these spectra, we get a good overview of the compositional diversity in the pyroxenes we're looking at. So when we do this for Mafic Mound, we see that the band centers for Mafic Mound materials exhibit a pretty significant overlap with the pyroxene band centers from the Mare and cryptomare materials. So this tells us that Mafic Mound pyroxenes are similar in composition to the pyroxenes in these basaltic materials. This group of materials exhibits a much different pyroxene composition than central peaks in SPA, which exhibit much shorter wavelength band centers, indicative of basically low calcium pyroxene. So now that we've established a general compositional overview of Mafic Mound, let's look in a little more detail at the geology of the feature. So here we've overlaid colorized Lola topography on a global WAC mosaic of the Mafic Mound region. So this view really nicely highlights the structure at Mafic Mound. So you can see that Mafic Mound is a fairly irregular structure. It's about 75 kilometers across. It exhibits a central circular depression, and the face of the feature is pockmarked with a number of craters of varying sizes and degradation states. So as Noah set up very nicely, this kind of hints that Mafic Mound might be fairly old compared to some of the other features in the region. So when we take a topographic profile of Mafic Mounds, we can see that very clearly the highest points of Mafic Mound corresponds to the rim of the circular depression. We see that the highest points of Mafic Mound are elevated by about 1 kilometer above the surrounding terrain, and the floor of the central depression is elevated by a little over 0.5 kilometer above the surrounding terrain. So given this circular feature at the center of Mafic Mound, we wanted to investigate a preliminary hypothesis that Mafic Mound could be some kind of pre-existing impact crater that was later filled by Mare basalts. So to do this, we did a compositional comparison between Mafic Mound and a suite of basalt-filled impact craters from within SPA. So we compared the band centers of spectra from a variety of locations across Mafic Mound to band centers from the basaltic fill, as well as the crater rims for, I think, around 15 basalt-filled craters from the central area of SPA. So what we see is that for these basalt-filled craters, there are clear compositional differences between the basalt fill at longer wavelengths and then the pre-existing crater structure at shorter wavelengths. For Mafic Mound, we don't see this type of diversity. If there was some kind of pre-existing crater structure at Mafic Mound, it likely would have been exposed by these several craters which are superposed on the surface. The fact that we don't see this type of diversity hints at the fact that Mafic Mound is compositionally homogeneous throughout the body of the structure, in contrast to these basalt-filled craters, which exhibit these clear compositional differences. So another comparison we did between these basalt-filled craters and Mafic Mound was in their topography. So here we're showing representative topographic profiles of 3 different types of basalt-modified craters from within SPA. So what you can see here is it's pretty clear that the crater floors of all of these modified craters are topographically lower than the surrounding terrain. So again, this is much different from what we see at Mafic Mounds, where the floor of the central depression is elevated above the surrounding terrain. Instead, Mafic Mounds looks topographically more similar to some of the smaller lunar volcanic complexes, such as Gardner and Mons Rumker. So as you can see from these topographic profiles, Mafic Mound is similar in both lateral size and vertical relief to these features, and they all also exhibit some type of central depression. One other observation we've made at the Mafic Mound area is using Grail data to look at the Bouguer anomaly. So in the global Bouguer anomaly map, if you squint, you can kind of make out a localized positive anomaly at Mafic Mound. But when you zoom in, you can see that there's this really nicely expressed positive Bouguer anomaly. So we're not exactly sure how to interpret this at this point, but we know that it does represent some kind of excess mass at some depth related to Mafic Mound. So given these observations, how might Mafic Mound have formed? So we've investigated 4 common lunar processes to assess their role in the formation of Mafic Mound. So we've looked at the possibilities that Mafic Mound could represent a basalt-filled impact crater, impact uplift or impact melting related to the SPA impact, or a magmatic construction. So while we've systematically ruled out the possibility that Mafic Mound is a basalt-filled impact crater, it looks like the positive topography, homogeneous high calcium pyroxene-bearing composition, and localized Bouguer anomaly are fairly consistent with a magmatic construction origin. So let's back up a little bit and talk a little bit more in general about lunar volcanism. So typical lunar eruptions involve very low viscosity magmas erupting at very high fusion rates. So this leads to the common occurrences of flat, smooth lunar mare deposits. Formation of positive topography volcanic constructs requires higher viscosity magmas and lower fusion rates. So this can result from things like lower magma temperatures, shallow magma chambers, and more silicic magma compositions. So of these processes, what specific processes led to the formation of Mafic Mound? So first, let's look at some of the observational constraints we have. So Mafic Mound, as we've seen, exhibits a similar pyroxene composition to the Mare basalt. However, there are these consistent brightness differences between Mafic Mound materials and the Mare basalt, which indicates a different mineral assemblage. So when we look at Mafic Mound, we're not looking at a typical Mare basalt. We're looking at some kind of unusual magma. And we also have the observation that Mafic Mound is located right at the center of SPA. So this hints at a relationship between the features. So we propose that Mafic Mound is a magmatic construct that's directly related to the formation and evolution of SPA. So we've identified two possible magma sources. So the first is some of the abundant impact melt that is expected to be produced during the SPA forming impact. Excellent work by Deborah Hurwitz and David Kring shows that for several scenarios involving the SPA melt, the evolution of the liquid produces a composition that's very similar to the plagioclase and high calcium pyroxene bearing composition we see at Mafic Mound. So it may be possible that at some point during cooling, crystallization, and subsidence of the melt sheet, some has erupted onto the surface to form Mafic Mound. Another possibility is that there's some kind of later melting induced by the SPA impact itself, unrelated to the impact melting. So in an impact of this size, some work by Elkins, Tanton, and Hager shows that you expect melting due to both decompression and possibly induced convection due to the impact itself. So while these melts would also represent partial melts of the mantle, similar to Mare basalt, it's possible that they might produce a somewhat different composition due to the different pressures, temperatures, and extent of melting you might generate in this kind of more unusual melting process. So to summarize and conclude, Mafic Mound exhibits several unique properties. It's an approximately 75-kilometer irregular feature elevated by about 1 kilometer above the surrounding terrain. It features a central circular depression that's also elevated above the surrounding terrain. Mafic Mound exhibits a homogeneous plagioclase and high calcium pyroxene bearing composition, and it's associated with a positive localized Bouguer anomaly. A constructive magmatic origin appears to be the most consistent with these observations, and we propose that the magma source is directly related to the formation and evolution of SPA. If this is the case, then Mafic Mound could be the manifestation of previously undocumented lunar magmatic processes. I will take questions. Thank you.
Yeah, Larry Taylor, University of Tennessee. Dan, what about the idea that this might be a some kind of fractionate, for example, a high silica fractionate, and you're seeing the major components, but do you see any sign of silica?
Right. So I've looked a little bit at the Diviner CF maps, and there's really no kind of anomaly that would indicate that there's really high silica content. So I guess right now we're not seeing any evidence for elevated silica in Mafic Mounds.
Misha Krislovsky, UC Santa Cruz. You showed similarity in topography with Peak Rumker and another guy. Mm-hmm. Could you comment about gravity signature, possible similarity in origin? Those two are not in centers of fault basins, if I remember correctly.
Right. Right. So those are, I haven't looked at the gravitational signatures of those yet, so that's definitely something we want to do, is to compare kind of the magnitude of the gravitational anomalies. There are also, there's a lot of complexity involved in interpreting the Grail data. So the fact that Mafic Mound is within this giant impact basin, there's this background effect on the gravity signature. So I don't work extensively with that data, so I'm not the one to interpret it. But that's definitely something I'm looking to do in terms of collaborations to look further into this as the project moves forward. The other issue is Mafic Mound is kind of on the smaller end of what gravity can resolve